years ago at Harvard University, and it's really nice to also be finally again. He grew up in New York, where he was educated in the City College of New York, now called the City University. Then he went to MIT, where he eventually ended up in particle physics. But he was always more interested, perhaps, in more philosophical questions, historical questions. So he was also teaching and working at the University of Massachusetts and Harvard University. And eventually, a few years later on, I don't know how much but in the end, the University College London, where he teaches since the early 90s. And, well, if you actually go to his webpage or Google it, you'll see he's written many interesting books about the history of science, Einstein and Picard, it's about imagery in conceptual developments in physics, and so forth. And as you see, he's written a book recently on the friendship, the exchanges between Pauli and Jung. So, legally translated.
Thank you, Luis. It's a pleasure to be here to lecture at a site that an establishment that Wolfgang Pauli was instrumental in founding, and was very happy when it was founded. And when the site was finally established in 1952, he expressed his admiration in a typically Pauli way. He wrote to the physicist Otto Stern saying that, well, this place is not so stupid after all, it'll mean jobs for theoretical physicists. And indeed, Pauli presented many interesting lectures to the theory group. And today I'm going to talk about what happened when the brilliant but troubled scientist Wolfgang Pauli met the great psychologist Carl Jung in 1932. The question is, can Jung's analysis of Pauli's dreams shed any light on how Pauli made his scientific discoveries? Let me begin by setting the stage with the standard science history version of how Pauli discovered the exclusion principle. Now, in 1913, Niels Bohr suggested a theory of the atom based on the iconic image of the atom as a minuscule solar system. The electrons were like planets circling the central nucleus or sun, and in Bohr's theory, the electrons were restricted to only certain orbits, which are labeled with the principal quantum number, a whole number, n equals 1, 2, 3, and so on. And when an electron drops from a higher to a lower orbit, the atom emits light, which is registered in the laboratory as a spectral line. Now, despite the magnificent successes of Bohr's theory, some deep problems remain in it. First of all, why didn't every electron fall into the atom's lowest orbit? Well, in 1922, Bohr offered a guess at the correct distribution of electrons in the allowed orbits, but he offered no details. And it goes like this. In the innermost orbit, or shell, labeled with K, there are 2 electrons, and 8, 18, 32. In other words, it's a series in 2 times n squared, where n is the principal quantum number. The other issue was when an atom is placed between the pole faces of a magnet, certain spectral lines split into several, called multiplets. Many sets of multiplets defied any explanation with Bohr's theory. This was called the anomalous Zeeman effect. Physicists obsessed over it, including the 22-year-old wunderkind Wolfgang Pauli, who finally became so disgusted that he just set the problem aside but kept up with the burgeoning literature. In 1924, while on the faculty at the University of Hamburg, Pauli had 2 brainwaves. The first was, what did relativity theory have to say about the predominant model of an atom with 1 free electron, the alkali atoms? Now, physicists studied alkali atoms with some intensity because it mimicked the hydrogen atom, which was the only atom that the Bohr theory ever had any real success with in a quantitative way. The alkali atom, in the models that were considered at the time, there was a closed inert core of filled shells of electrons, and then the entire chemical activity of the atom fell on the shoulders of the free electron. In order to explain the anomalous Zeeman effect, Bohr proposed that the inert core could be distorted in 2 ways by a vaguely defined force, and the factor of 2, or 1/2 to be more precise, was indigenous to all closed core models. But Pauli found that electrons in the closed core can move at speeds close to that of light. this should affect the spacing between the multiplets, disagreed with laboratory data. In his inimical way, Pauli declared that core models were useless. The second brainwave requires just a word of background. The state or condition or position of an electron in a Bohr atom depended on three whole numbers called quantum numbers. That was reasonable that it should depend upon three numbers because after all the electron moved in three-dimensional space. Enter Edwin F. Stoner, who was a physicist at the University of Leeds, and by a joint manipulation of the three quantum numbers, Stoner found a way to associate the number of multiplets in an alkali atom undergoing the anomalous Zeeman effect with how the electron shells fill up. And that was as far as he went. Enter Pauli. Pauli realized how to extend Stoner's result beyond the anomalous Zeeman effect by allocating to each electron the two-valuedness of the useless core. He did it as follows. He assigned to each electron in the atom a fourth quantum number with a value 1/2, which was soon to be associated with the spin of the electron. Ergo, the exclusion principle followed. As you know, no two electrons in an atom can have the same four quantum numbers. This tells you how the electronic shells fill up the way they do, so substantiated Bohr's guess, and also enabled scientists to begin to understand the periodic table of elements, and it had cosmic consequences. It told you not only why metals are hard, but why certain stars die as they do. For example, white dwarfs. So that, in a nutshell, is an outline of the science of Pauli's discovery of the exclusion principle. But one would like to know more. One would like to know how he discovered it. What was Pauli's mindset at the time? And in particular, why did Pauli angst over going from 3 to 4 quantum numbers? Now, although Pauli was a great compartmentalizer, could it have been at the moment when he made his creative breakthrough in December 1924 that the watertight compartments in his mind broke down? Now, Pauli, there are two sides to Pauli's personality, it turned out. By day, he was a straight arrow, Germanic, Austrian hair professor doctor. By night, it was another story, as he revealed to Jung some years later. The specific threat to my life has been the fact that in the first half of my life, I swing from one extreme to the other. In the first half of my life, I was a cold and cynical devil to other people, and a fanatical atheist, an intellectual intriguer. The opposition to that was, on the one hand, a tendency towards being a criminal, a thug, which could have degenerated into me becoming a murderer, and on the other hand, being detached from the world, a totally unintellectual hermit with outbursts of ecstasy and visions. By night, Pauli often went down to the St. Pauli, the notorious red light district of Hamburg. There, the main attractions were not on the main street, the Reeperbahn, but on side streets such as the Grosse Freiheit, which was Pauli's favorite side street, lined with rough bars and teeming with, and with cabarets crawling with women. And there he found the means to alleviate his personal anger and the strains put on his psyche by a life devoted to physics research in which he deemed he was failing.